All right, good afternoon. Welcome to EfficientML.ai lecture 16. Today we are going to introduce diffusion models and how to accelerate diffusion models with advanced techniques. So in the last lecture, Ji introduced the deep generative learning. So we first sample from a data distribution to obtain a network. And later, after training this network, we can use the network to predict new images, new contents. So that's generative learning. Comparing this kind of descriptive model versus generative model, a descriptive model gave a input and trying to classify it, trying to predict the bounding box, trying to predict the pixels, the sentiment. So we are given the text or input, trying to predict its attributes. So trying to make a decision boundary. On the other side, the generative model is giving a label, giving a class, giving a condition, the text. We try to generate the content, the image, the text. So trying to model to learn the probability distribution of the data. So there are lots of popular applications using the techniques that we are going to learn in this lecture, such as Adobe Firefly, the Midjourney, DALL-E 3 for those content generation. So a lot of applications by using the diffusion models. So there is a pretty wide range of deep generative learning approaches. So today we are going to focus on the diffusion models. And this is the agenda for today's lecture. We'll start with the basics of diffusion models, introducing the denoising diffusion models, and also how to add condition to the diffusion model, latent diffusion models, how to use it to edit the image, and also personalize the model. And then we're going to talk about acceleration techniques, how to reduce the number of steps by using fast sampling techniques like DDIM, and also by using progressive distillation to get fewer number of steps, and also using guided distillation to reduce the number of feed-forward iterations. And also those acceleration techniques by using sparsity and by using quantization to accelerate diffusion models. We're going to see some domain-specific techniques, although we call it sparsity and quantization, they're actually quite different, some unique techniques in this domain-specific setting. So let's start with the denoising diffusion models basics. There are two concepts. So the denoising diffusion probabilistic models, short for DDPM, basically consists of two processes. So the first process is the forward diffusion process, when we are gradually adding noise to the input. The input gets more and more noisy. And there's also the reverse path. This reverse diffusion process is generating the image from the noise. It starts with the noise and then gradually denoise to generate the data by denoising. Compared with GAN models, which we learned from the last lecture, this kind of forward process defines an iterative mapping process, not just one time, but iterative mapping from data distribution to a Gaussian noise. And this backward path learns to reverse the forward process step by step. So learn very fine grained those details step by step. Rather than GAN, you just do it once. So this is some illustration about the forward process and also the reverse process. In the forward process, we can see we destroyed the data. Original image, we destroy the data by gradually adding small amounts of noise. So starting with clean image, and in the end, it becomes Gaussian noise. Compared with that, we have the reverse process, starting with noise and gradually denoise to create data by gradually denoising a noisy code from a stationary distribution. So starting with pure noise, and then we denoise to get the original, to get the target desired image. So in this forward process, we can model the relationship between xt and xt minus 1 as a Gaussian distribution. So the mean, this is the mean, this is the variance. So beta is a predefined constant to control the diffusion speed, which is only related to t, okay? And it's linearly growing with the time step, gradually adding more and more noise to the input image. So this is the relationship between adjacent two steps, xt minus 1 and also xt. Okay, what's the condition on xt minus 1 to get xt? But how do we sample xt directly from x0, okay, from x0 to xt? So we can do a little bit of math. Don't be afraid of it. I'll walk you through. So here we plug in the equation. This is the mean. This is the variance. Okay, this is following a Gaussian distribution here. The relationship between xt minus 1 and xt is like this. These are constants. Beta is only related to t. We can do a little transformation, define alpha t equal to 1 minus beta t. So we can transform the relationship into the second row. And then we can plug in xt minus 1 using a similar form. Okay? The relationship between xt minus 1 and xt minus 2 can use similar form of equation so that we can get the relationship between xt minus 2 and also xt. And here is epsilon t minus 2 is also following a Gaussian distribution. So now we have two Gaussian distributions, epsilon t minus 1 and also epsilon t minus 2. So adding two Gaussian distributions, basically the variance, we are adding the variance together and square it. And so that we can merge these two terms together into a single term, and we put a bar here to distinguish them. Okay, so we have a single Gaussian term here, and the beginning term stays the same. We can repeat this process on and so on until we reach x0. Okay, so it's an iterative process from xt to xt minus 1 to xt minus 2 and all the way to x0. Okay, and you have a chain of alpha t minus 1 all the way to alpha 1, together with a Gaussian distribution here. We define a new term for this combination. This alpha multiply them together, we denote it as alpha t bar. Then we can plug it, simplify the writing. The relationship between xt and x0 is like this, so that we can get the relationship from x0 directly to xt. Okay, it's a normal distribution. This is the mean. This is the variance. So we can directly get from 0 to a certain time stamp. And just rely on these two definitions, alpha t and alpha t bar, so that we can get, just repeating the equation from the previous slide, the relationship between xt0 and also xt, as this is the mean and this is the variance. We call it a diffusion kernel. And this is what alpha t bar looks like. As t goes on, it's gradually diminishing to 0. So for the sampling process, we know x0, so we can get xt. This is the relationship. And here we are having a normal distribution in the back. And beta t is designed such that alpha t is close to 0 when, and also the relationship between x0 and xt is following a normal distribution. So alpha t, when t is getting large, it's close to 0. So let's now see the reverse process, the reverse denoising process from xt all the way to xt0. It has to assume when beta t is small, the relationship between xt and xt minus 1 is also a Gaussian, so that we can write it in this format. This is the mean, this is the variance. The mu theta xt is the mean, which we are going to predict, and it's learnable. Actually, that's where the essence of this class. So, and here we defined sigma t squared to be equal to beta t. It's a little bit of math, but we'll go to them relatively quickly since we are focusing on the engineering aspect. So this is the loss. We're trying to define the loss so that we learn how to train it. So this is the minus log p x0. X0 is the real data. We want to maximize its log likelihood. And by using this evidence lower bound, we can find the bound which we are not going to put them in this lecture. By using this is basically the joint distribution from x0 all the way to xt, and this is the loss function we are trying to minimize. Omitting some linear algebra, we can simplify that into 3 terms. Since here this equation is parameterized by theta, the first term is not related to theta, so we only focus on the second and third term. For the relationship between xt0 and also xt minus 1, we can use conditional probability to simplify it in this way. Okay, so this is the Gaussian. The other term we have seen before from t to t minus 1 is also a Gaussian. Okay, so both of them are Gaussian so that we can further simplify that. And this first term can simplify them in a similar manner. So let's first try to simplify the middle term, and soon we are going to see how to map this into PyTorch language. If you're not comfortable with the math, don't worry about it at all. Omit some linear algebra. The loss function is basically this square term. And trying to minimize this square term, we want to make this mu theta xt equal to this big term, so that you have the square that is minimized. Notice this epsilon is the noise. The added noise is the only unknown. So that's the goal our neural network is going to predict. Okay, so epsilon theta is the parameter of the UNet. Is trying to predict the added noise. So all what we're doing by deep learning is trying to predict the noise. Okay? Predict the noise given the input. Given a noisy image, we try to predict the noise. Okay? And we subtract the image, subtract the noise from this image, okay? And then we're trying to get this mu theta so that we can plug in this mu theta back into this equation. And assuming this relationship from x0 to xt during the forward process, we can plug it in to simplify it in this way. Okay? Lt minus 1 can be simplified in this way. So this L0, which is right here, also have a very similar form. So now we get a relationship. Okay, given an image, we try to predict the noise using epsilon theta. Epsilon theta is the UNet, where the bulk of the computation is spent on. Okay, and we try to predict the noise and use that as the loss term. So writing that again, we uniformly sample from 1 to t, and also sample a correct image, target image, and also sample a Gaussian noise. And this is the ground truth noise we are trying to predict. And this is the function, the UNet. We are trying to apply a neural network. Given the input, we are trying to predict the noise. And this is basically xt, the input, calculated by the diffusion kernel using x0. So we simply set lambda t equal to 1 for better perceptual quality. And so far, lots of math, but everything can be condensed into a very intuitive image. And this is what I want you to remember, not the math equations, but this intuitive picture. Let's walk them through carefully. So given x0, okay, and multiply with a constant term, this is what alpha t looks like, with t is getting smaller and smaller. And this is a random noise, random Gaussian noise, multiplied with 1 minus this term. Okay, and then you add them together, you have a noisy image. You can still tell it's a cat, but it's added a lot of noise, and you pass this through a UNet, okay, down sample and then up sample, pass through this UNet, trying to predict the noise. Okay, so all we are doing here everything unique in this lecture is that we are doing a pixel to pixel-wise prediction. Given a noisy input, original input, noise, noisy input, given a noisy input, trying to predict the noise. How to predict it? By matching that with the noise you added to the input image. Okay, so that's how we closed the loop. Okay? Given a noisy input, trying to predict the noise that was added to the image. Okay, so we can make it a lot more easier to understand. Let's see the training algorithm. So we uniformly sample a t from time 1 to time t, and then we sample an input image, such as a cat. It can also be a dog, as long as from your desired distribution. And then we sample a Gaussian noise, okay? And we get the xt following this equation. This is the original input image, okay? Original clean image, and this is the noise. This is the noise, okay? And add them together, we have xt. Okay? Add them together, we have xt, and we feed this xt to epsilon theta. What is epsilon theta? It's a U-net. Theta is the parameter. It can be tens of millions of parameters. This is epsilon theta. Okay, we feed it to the epsilon theta, and it's also parameterized by t, since during different timestamps it can be different. So we pass this xt through this U-net and trying to predict a noise. Okay, we are trying to predict a noise, and we are trying to minimize the difference between the predicted noise versus the original noise. And that's all we are doing as a loss function. That's all what the equation previously is about. You want to predict the noise.
But would it be the same if you try to predict the image and the network?
I don't know if that works.
There is something about that.
Right, and these terms, you have to be very careful. That's all what the revision is about. Yeah, so this is the training algorithm. And let's see, what about a sampling time? What do we do over there? So let's again start with the intuitive image. Okay, so we have a noisy image. We try to get a clean image. And what do we do here? Again, pass it through a U-net, okay, and trying to predict the noise. And we subtract the noise. Of course, there are certain terms right here. Those are just constant. With respect to the t. Okay, so this is alpha t going down linearly. This is alpha t bar, multiplying them together, close to 0 in the end. And this is sigma t square going to increasing. So this is these constant terms. So the essence is that we are trying to subtract this noise from this noisy input. Okay, the U-net is predicting the noise. We are subtracting the noise from the original noisy input and trying to get a denoised image. But here, interesting part, here we also added another Gaussian noise. And then this is becomes the next time step, xt minus 1. Okay, so this is xt noisy image, xt minus 1. Still a noisy image, but less noisy. We'll just repeat this process until it gets a completely clean image. Okay, so this is an intuitive image. I hope you can remember. And on the right-hand side, you can naturally translate this into the algorithm. Okay, so starting with xt, which is completely random noise. And then from t to 1, we are doing the reverse process. So this is from t to 1. We sample a Gaussian noise, which is here. And then we use xt as input, feed it to the U-net, which is epsilon theta. Theta is the parameter in our U-net. Use the U-net to predict the noise, and use xt to subtract the noise. Okay, and that gets this term. And finally, we added the Gaussian noise to get the next xt minus 1. From xt minus 1, we continue in the for loop to predict xt minus 2 and until x0. So that's the denoised image we are going to return. So that's the same thing where this equation is about. So hope you can remember the equation and also both the equation and also the intuitive illustration of this process. So where is the bulk of the computation? It's here. It's the UNet. Although area-wise it's small, but actually most of the computation is going here. It's a pixel-wise prediction. Given a noisy input, predict the noise. You have large resolution here, then you have large resolution here. Okay, so that's where the bulk of the computing is going. And these are all like pixel-wise subtraction. Okay, pixel-wise addition doesn't have a lot of computing. All right, so using diffusion model, these are some of the examples emerging as powerful generative models, outperforming GAN sometimes, some cool images. All right, so what if we want to generate a specific stuff, like particular class, or given a text to generate the image? Oh, so there's a metric called FID. People use that. So previously we generate a lot of generated image versus real world image and measure the similarity with the pixel-wise difference with the real world image. You can check out FID for that. All right, so it's about how do we add condition, right? If you use Midjourney, you want to type into some words to generate a moon, generate something, a horse riding a moon, right? So how do we add those conditions? We call it condition. Okay? So unconditional generation is basically using this term. And if we compare with the conditional generation, the xt minus 1 not only depend on the previous xt, but also depend on the c. C is the condition. Okay? So here we have mu theta not only as a function of xt, but also as a function as this condition, and that's the only difference. So here, the UNet previously has only one input, which is the xt. Now it has not the t, but now it has another input as condition, which is the text or the image or the class label you input as a condition. Okay, so this epsilon now has three parameters: the image, the timestamp, and also the condition. So let's see what kind of condition types are there. Okay, we can have a scalar condition like a class, generate me some dogs, generate me some cats, class ID, just a single scalar class ID. We can also have pixel-wise condition. Okay, pixel-wise condition like so this should be actually this should be text condition. There's a typo here. This should be text condition. Okay, a sequence of text tokens, like a photo of a moon gate. Gee, make sure you edit, polish the slide to fix. This should be text condition on the slide. Okay, this is what very widely used Midjourney these days. Like you give a text description what you are trying to generate. The next one is the pixel-wise condition, like giving a mask, like a mask of a cat or a canny edge of a building. So pixel-wise condition. So let's start with the scalar condition, like a class ID. Okay, so this is the original feature map, and we want to add those class condition to the feature map. So we pass it through an encoder so that we can get a representation by batch size versus C. C is the number of channels. Okay, we pass it through the MLP to match the number of channels to be the same as the feature map. So here we have 4 channels. The embedding here should also have 4 channels. So the C here matches with the C here. And then we can do a broadcast add. Okay, broadcast this pixel to the entire XY location. Similar for this pixel to the second channel for the entire XY location, so that we can get a conditional feature map. This is the simplest method to add a scalar condition. A more improved version is basically double that. Okay, we have not only addition but also multiplication. So we predict a scale and also a bias. Okay, to scale the feature map and then add the bias. That's why here we have multiplication and addition. So that's how we insert the scalar class condition. Okay. The next is the text condition. How is Midjourney handling the text we input to the image? So that's using a cool technique called cross attention. Okay, so we have the input feature. We talk about VIT. We chop the image into several patches, and each patch becomes a token. So that's the queue, that's the query. And K and V are basically the text conditions. Like photo of a moon gate. This is the text we feed to Midjourney. We treat them as K and V. Okay? We use pass it through a W matrix to transform it to get the feature as K, and pass it through the WV to project it as the value. And then we pass it through attention. Why we call it cross attention? Because some of them is coming from image, some of them like K and V is coming from the text. Well, Q is coming from the image. And then we pick each patch, each token from the image, and to multiply with the K to get the similarity, to get the attention. And we use softmax to make it sum up to 1. And then we use that as the weight to get a weighted average of the V of the value. Okay? And this becomes a output token. So we can repeat this process through all the input image tokens and to get a output image. So this is how cross attention works by using the Q transpose softmax sum up to 1, scale it by dimension, and then times V to get the text information injected into the image. Okay, so there's a text information injected into the image. So finally, the output token is an image token. You put it back, it becomes the mingled text and image. This is a very effective way to mingle the text with image by using cross attention. Okay, so the last type, how to inject condition, is by using this pixelwise condition. So a very intuitive way, for example, we want to generate a cat that looks like in this position, it looks like this. So we can just put the segmentation map concatenated with the noise, okay, and trying to predict the noise. Very simple, just concatenate. Are there better methods? One of the represented one is the control net, which got published in ICCV 1 month ago. Very fresh, very widely used technique. It's actually pretty cool, given the input canny edge. This is default generated here. You can also input the text condition like masterpiece of fairy tale, giant deer, golden antlers, and Queen City Gaelic something. So all the generated image looks like the canny edge input, canny edge condition. Okay? Or we can input a human pose. Human pose, again, it's a pixelwise condition. I make sure the generated man all follow this gesture, follow this pose. Okay, you can generate default. Hand is here, exactly following the condition, or chef in kitchen, or Lincoln statue. You can have not only the text, but also such pose condition and also canny edge condition. And they all look very similar in their pose. And how is that achieved? Okay, so it's very interesting by using control net. This before you have a neural network block. What we added here, we fixed this original neural network block, but make a copy, okay, make a trainable copy, initialize the same way as the original neural net block. And we add a zero convolution before and after. It's a bit misleading by talking about zero convolution. In fact, they are zero initialized one by one convolution. So initially they are zero, but after training they may not be zero. Why initially they are zero? Because as if you don't have this branch. Adding this zero branch, injecting the condition, initially they are not injecting anything because they are initialized with zero. So it's just using this main branch in the beginning. But after training, this convolution, they are both one by one. They are no longer zero, so that they can inject the condition from the top. That's the key idea from ControlNet. And we can stack multiple such blocks together. So this is the original UNet, okay? Downsample, upsample. So in the downsample phase, we are going to add the control branch. Okay, so this is could be the pixelwise conditions like the pose map. Can also be the semantic mask. Can also be the canny edge. We show like the edge of the canny edge of the deer as an input image, pixelwise. Okay. We pass it through the zero convolution, and this is the original condition we inject by cross attention, like text prompt. We have seen the Lincoln statue text prompt. This is still using the cross attention to inject those text condition. And then we copy the downsample stages from the original, this is Stable Diffusion's encoder block. We copy them. And then on the upsample stage, they don't have any, they are directly using zero convolution to feed it back to the original upsample phase of the Stable Diffusion's decoder. So this is how this pixelwise maps, either semantic mask or canny edge or pose, those conditions are injected. Okay, copy another branch, initialize with a zero, and this is copied. This is initialized with a zero. Feed it combined with cross attention with the original text prompt and feed it back to the original main branch. Okay. Throughout the training, the main branch is fixed. You don't touch the main branch, but only this side branch to inject the condition. Okay, so that's ControlNet. And now we want to talk about how do we trade diversity for quality. So we want to also generate a specific class. Okay, so we talk about we can not only given the class we can get an image, but also we want to make it follow this particular class. So we want to train a classifier at the same time as the generator. Okay, so we add not only the original gradient, but also the classifier's gradient. Okay, and then the new sample distribution is defined as this is just from this class to generate this xt, but also this xt should be predicted as this class, and we put omega as the strength to control the relationship, the strength. So this original sampling plus the classifier's gradient to make sure the generated image will be classified as the original desired class. And we have a guidance strength omega on the top. So if you put them in the log space, this multiplication of these two terms becomes the addition. That's why we put omega on the top, because getting the log, they become a multiplier in the front. Okay, what it means to our diffusion equation is that basically we add another term, okay, another term to the prediction. Okay, so this is the original naive conditional sampling. We have a condition t and xt, and trying to predict the noise. This is subtracting the noise and get the next step. Okay. And later, we not only predict the noise, subtract the noise, but also we added another term trying to minimize the loss, trying to make the classifier, we can classify this xt as a desired class. Okay? So that's the new classifier gradient that gets introduced to make sure the generated image, they all belong to the same class. Okay? We want to encourage the loss such that the generated image is all predicted as the desired class C in this case. And actually, it's pretty effective. Like if omega is pretty small, okay, there are some dogs, but not all of them look like dogs. Some of them doesn't look like dog. But if omega is pretty large, meaning that we want to make sure the loss of the classifier is pretty small so that all the generated image look like dog. It actually looks like dog a lot. What are the limitations here? You train a classifier, it can only do classification. So it can only work on class condition. But how about text condition? How about pixelwise condition? It's not straightforward. And also they need to train an additional network, a classifier, okay, which is complicated. So how do we solve this problem? So let's look at, rather than classifier guidance, let's look at classifier-free guidance. Okay, so to support diverse condition, class, text, or pixels, okay, no extra, don't need to train any extra classifier network. Okay, follows Bayes' rule. Given xt, I want to predict the C. I have rewrite it in this way. Okay, this is a conditional model. This is an unconditional model, which hinted that now we want to forward the neural network twice. One is a conditional model. The other is an unconditional model with C and without C. We want to double the flops. Later we are going to talk about how to reduce the compute over there. So if you expand our previous equation defining the classifier guidance, remember there's an omega controlling the strength of the original loss versus the new classifier introduced function. So we can further simplify that by using Bayes' rule in this way. Okay, we can see there are two terms. Okay? In the log space, if we expand it, it'll be this one subtracted by the second term here. One is conditional, the other is unconditional. Okay, one is conditional on C, the other is not conditional on the C. And here we have omega plus 1, and here we have omega. And then if we continue to derive the equation for the classifier-free guidance, we can compare that with the original conditional training. It's actually quite simple. So during training time, we just sample the condition. Okay, previously we have this this condition. We always have this condition. Given x, given t, given c, we try to predict the noise, minimize the distance, and now with probability unconditioned, okay, we randomly drop the condition so that we can train it unconditionally. So C here has some probability to be none, adding no condition. Okay, so that's the only change, and C here is the same as the C here. Okay, so that's the only change. We during sample we sample with some probability that the condition is none. What about at sampling inference time? At inference time, remember we have these two terms. One is conditional, the other is unconditional. Okay, the constant here is omega plus 1. Here is omega. Okay, remember the term here, omega plus 1 and omega. So that's the only change we made here. At inference time, we have to run the inference twice. Okay, combine the results of conditional and also unconditional forward process. Is doubling the flops. We have to do the same, run the same network twice. Okay, the networks epsilon theta, they are the same. We have to run it twice. And this is the result from no guidance versus with guidance. Okay, such large W usually lead to better quality but less diversity. So the advantage of such classifier-free guidance is that it can generate to any conditional form, not just class, since we don't need to train a classifier. Okay, no need to train an additional network. So this condition, if you see the previous equation, It can be anything. You can use text condition. Remember, we talk about cross attention to inject the text condition. Okay, and also we can use the pixelwise like a mask condition by using the control net. Okay, so this is very simple. Just use with the condition. So without the condition, it can be any method we have learned so far to inject the condition. Okay, not necessarily relying on it has to be a class. So this C can be any condition using the method we learned to inject the condition. And the only catch here is that we have to forward the network twice. All right, so that's a lot of content. Let's take a 5-minute break before we jump into latent diffusion models. All right, welcome back. Let's continue the discussion. So diffusion model seems pretty complicated math, but all we want to remember is that what we are predicting, we're predicting the noise. Okay? So classification network is predicting a class. Detection network is trying to predict the bounding box. Segmentation model is trying to predict the mask. Diffusion model is trying to predict the noise. Why do we need to predict the noise? Because then we can denoise. Okay, that's the essence of the diffusion model. So let's continue to talk about the latent diffusion models. So when we have a high resolution, how do we generate a pretty high resolution image without incurring a lot of compute? So we first pass through the image into a pre-trained variational autoencoder to encode it into a latent space, which has much smaller resolution, like 1/4 or 1/8 of the resolution. Okay, and we run the diffusion process in the latent space, and then we use the other half of the variational VIE, the decoder part of it, to try to reconstruct the image. Okay, so rather than running the diffusion on the original pixel space, we run it in the latent space. So the advantage that applying to the latent space is we can have simpler denoising because the resolution, the dimension is much smaller, and also can lead to faster synthesis. That's actually very widely used. And algorithm-wise, it's actually just one line of code here, very simple. We just pass the original input image into an encoder and get a latent space. And we run the diffusion process in the latent space. Okay, so we add noise, pass it through the UNet to predict the noise and try to minimize the loss. The only difference is here. We pass it through an encoder to make it have a lower resolution. Similarly, for the sampling stage, rather than directly get the output, we pass it through a decoder to get the output. Everything before is exactly the same. Okay? So we have the noise. We use the UNet to predict the noise, subtract the noise from the original input. We add the noise, trying to get the next time step. And finally, for Z0, we pass it through a decoder to reconstruct the original input. So this is widely used, like Stable Diffusion XL. They're using such latent diffusion method, like astronaut in a jungle, code color palette, and also a deep sea diver floating. These are high resolution images compared with the cats and dogs we've seen before. The image resolution is much higher quality. They're all using such latent diffusion methods. Question? Certainly. How do we edit it? That's exactly the next part we are going to talk about. How do we edit the image? Like we can draw something, draw a tower, draw some trees, draw a bedroom, draw some scenery, okay? And how do we use SD edit to actually get the corresponding picture that's associated with this hand stroke-based editing? So the idea is that we use our hand to draw something very naive, like roughly a tower, some cloud around it, and base on the bottom. So that you assume the image distribution is here, our stroke is here. there is some distance, and we add some noise to perturb it with some noise. Okay, so the stroke becomes noisy, And the good part is that you can assume this is a certain point in the diffusion process, and then we can predict the noise from here and gradually remove that predicted noise. And this center, this mean, will shift from here and gradually shift toward the original image, the real image distribution. So it looks like a real image output. Okay, you first add a noise and then predict the noise, then subtract the noise. And that's the magic about how do we convert this stroke into the image. So this stroke-based editing. We can also do image-to-image translation. The original hand-drawn picture, and then this is the generated picture. Again, we add a noise, and then predict noise, and then denoise, so that we can shift the distribution from this hand-drawn image to the desired target style. What about text-based editing? Like here, the boulevard are crowded today. How can we tone down this crowded, make it less crowded? A lot of people here, fewer number of people. A photo of a cat riding a bicycle, and change it to a photo of a cat riding a car. And then here, this is just image, and then we want to add a style, children drawing of a castle next to a river. Immediately turn the castle river into a children's style. Or we can add some jelly beans to the cake. And this looks like magic. How is that achieved? Remember, how did we inject the text prompt? By cross attention, right? What is cross attention? Reminder, let's go through it again. So the pixel features, we chop it into different patches. Each patch is a token that becomes the query, the Q, and the key, and the V are both from the text. For example, here, this is a prompt sentence, several prompt sentence. And you get an attention map. For each query, you get an attention map. So here, since you have 5 text prompt tokens, you get 5 channels in the attention map. You multiply by the V. V is from the text, and then you get a target output. What about we do some manipulation for the words, like removing bicycle and change it with a car? Everything else is the same. So here we want to just use the original cross attention map from photo of a car riding a bicycle, so that the location of the bicycle remains the same. So here, up to here, everything is the same. We just plug in the new V. Okay, the V, the last one of them is a car rather than a bicycle in this case, so that the cross attention map determines the location. The location doesn't change. The thing only changed is the V. So that original attention cross attention stays the same. Only use the new V from bicycle to car. What about this case? Adding jelly beans, okay, to the decorations, adding some words. Okay, so here we add a new phrase. So the old words will use the original cross attention map from old to new, and the new words use the new map. Okay, so new words, okay, longer number of tokens in the key, so the attention map has more channels. The V also has more, so you have a couple of new attention maps. What about getting different weight, like tuning down the crowded, make it less crowded, or make it more crowded? So we can simply reweighting, adjust the magnitude of a specific token. Like here you have 5 tokens, then you have 5 channels in the attention map. You want a particular token to tune up or tune down, you can weigh it, tune it up, or tune it down for the certain corresponding channel in this way, to tune it up or tune it down. So that's how to edit the image. How to personalize the image. Say, want to draw a picture of this is my or someone's lovely dog. We just want to draw a particular dog in different places. Acropolis, in the doghouse, in a bucket, sleeping, swimming, but everything is not the general dog, but it's my dog. It's a specific dog that should look like this. So Dream Booth is doing that, which is actually a challenging task. For example, given the input image, which is a clock, very unique clock, 3 is written in this way, a very artistic style. But DALL-E 2, using the image guidance, is not generating something exactly looking at my clock. The 3 is not the style I want. And also, we want to change the background. This is probably on the bad, but also I put it in the context of some green outside. But this one is following the context, but the fidelity is poor. The 3 is in the middle. It's not like 3 here. But by fine-tuning, we can generate the same clock, okay, in the background of several green outdoors. Okay, you can make it both maintain the fidelity and also use new context. And how is that achieved? So Dream Booth basically fine-tune the model. Okay, the model takes it's a text to input to image model. Okay, so we have a couple of training data saying this is a dog, this is the dog, this is the dog, and we put it to fine-tune this model so that it can generate a customized model. Okay, generate a customized model, no longer the original general text to image, but this is a personalized text to image, just one model for one object. Okay, you have a dog, you can train a new model. But later you want to say make an advertisement for another stuff, you have to fine-tune another personalized text to image model. Okay, so the input is just few images of a specific subject and the class name, and the process is basically fine-tune the text to image model to create a personalized version of that particular subject. And output is a new model, okay, capable of generating images of that subject in different contexts. And the limitation is that you need one fine-tuned model. It's only specific to one subject. So here, like, I train a personalized model. A V dog is in the beach. A V dog is walking in a colorful carpet. Another limitation for like Midjourney is that I cannot generate faces like what we want. Like Fei Fei is riding a horse. Lady doesn't look like Fei Fei, right? But existing work either need actual fine tuning, right? Like the Dream Booth, you need to fine tune the model, which is costly as we learned. Or I can generate poor multi-person like Newton and Einstein. We want them to sit in the park. They get mingled together. It looks like each other. Or using our approach, you can distinguish them rather than mingled together. Or overfit the reference image. So like Fei Fei riding a horse, we just have Fei Fei but no horse. But now we want to generate something like this, Fei Fei riding a horse. How is that achieved? Looks like a bit complicated, but let's walk you through that. A woman and a man standing together. So we first get the picture, taking a picture of the two subjects, and find a segmentation mask. This can be easily obtained using auto annotation tools, for example, using SAM. And then you give the text prompt, pass it through the text encoder to get the text embedding a woman and a man standing together. Okay, and you pass through the image into the image encoder, like the clip image encoder, and we concatenate. Since we know the man corresponds to this image, the woman corresponds to this image, we concatenate the features from the text embedding with the subject embedding. Okay, and then we get a conditional embedding. So red and green correspond to red and green here, and then we inject the conditional embedding by cross attention we learned using the UNet. Okay, so we fine-tune the UNet, fine-tune this projection, fine-tune the encoder such that it can learn that we should match the cross attention map for woman and man to be in this location rather than mingled together. Okay, so we are trying to minimize the distance between the woman's cross attention map with woman segmentation mask, since we know the woman should be here and the man should be here. Okay, so by using such cross-attention localization, we can solve this problem where peoples are entangled together. So at inference time, again, we have the text prompt, pass it through the text encoder, we get the tokens. Image, through the image encoder, we also get the tokens. We add the corresponding man into the text with the image. And the trick here is we need a delayed subject in condition. So in the beginning, okay, this is in the beginning of the denoising step, we only take the original pure text prompt to make sure it's indeed someone sitting in the park. And only later we want to refine it such that it's Newton and Einstein sitting in the park. So later we take from this side Newton Einstein. So that the generated image can have a good trade-off. So this is about the cross-attention map. Make sure without the localization and with the localization, we want to make sure the man correspond to the original image. And this is the trade-off when we should inject the subject conditioning. In the beginning, we don't inject the subject conditioning, just make it general, make it indeed someone riding a horse. But now we want to later inject the subject embedding condition such that it looks like Fei Fei riding a horse. Okay, so there is a trade-off. If alpha is too large, it looks like Fei Fei. If its alpha is too small, it looks like a horse, but doesn't look like Fei Fei. Only something in the middle, we can make it have a great trade-off. So these are the several examples cooking together. This is mingled, but this is not mingled or Yang in a different style, in the wood style. So this is Hinton and Jeffrey, Jeff Hinton, and also some Newton Einstein in the park, etc. But there's a generative learning trilemma. 3 aspects you cannot get both. Like GANs, you get high quality samples, you get fast sampling, but the convergence is hard. Diversity is not good. Diffusion models have good quality and a good convergence, but it's pretty slow. Okay, and variational autoencoders, they have this fast, they converge well, but the quality is bad. So now let's talk about how to try to solve this trilemma. Okay, especially for diffusion models, which already have good convergence and good quality, and how to make it faster. Since naive doing the vanilla version require 1,000 iterations, lots of network evaluations. So let's talk about fast sampling techniques to make it faster. Let's first talk about DDIM, denoising diffusion implicit models. So rather than each step, we just denoise a little bit, can we have a larger step size? So directly skip the middle 2 steps, have the 4th step, skip another 2 steps, directly get a clean data. But that requires more complicated functional approximations. So the original DDPM we learned so far assume is Markovian, right? So the next t only depends on the previous time step. Okay, that's how we get this equation. Okay, so we only use these properties during training. To get a trained model, can we design better sampling methods to use the same pre-trained model but use less number of steps? Okay, is it possible to define a non-Markovian forward process and corresponding reverse process but share the same diffusion kernel and loss so that we can reuse the same model without having to retrain it? See, now not only depend on xt minus 1 but also x0. In the reverse case, now xt minus 1 not only depend on xt but also x0. They also satisfy the original terms here. So we can make it a quick result here. The DDIM on top of DDPM will get changed here is that DDPM, the xt minus 1 is related to xt, but now it's not only related to xt but also x0. and x0 is actually estimated. Okay, x0 is estimated from xt. Okay, so that in this way we can reduce the number of steps. So now we sample this tau, okay, tau 0 to s, like from 0 to 10 to 20, 30, all the way to 1,000. So this it skipped 10 steps in the middle, making the total number of steps a lot less. So compared with, this is the original DDIM sampling, this is the fewer step DDIM sampling using the T and T slash right over here to reduce the number of steps. And we can see this is the Sparsity using 10 steps all the way to 1,000 steps using DDIM. With 100 steps, it's already have a pretty good FID. The lower the better. Well, the DDPM has a pretty high FID. Like with 20 steps, the DDPM barely just doesn't work. Pretty high FID, but DDIM is already giving a pretty good FID. Although in the end, with the same number of steps, you cannot converge at the same quality, but with fewer number of steps, this is super promising. Similar for Celeb-A data set, with about 20 steps, you can already beat the baseline DDPM a lot better. The reason is that DDPM, the equation hold only when the beta t is small. So each step, you cannot move too far, cannot have too much noise. But DDIM does not rely on the assumption where beta t should be small. If you're interested, there are more advanced samplers you can check out, like DPM solver, other work. So now let's talk about another technique, progressive distillation. So we have learned distillation, we have a teacher model, we have a student model. Student model try to mimic the teacher's model. But now here we try to have a student model, 1 step, to learn the teacher model, 2 steps. Okay. Condition is that it has to be deterministic, which is very important. So we can use DDIM rather than PDPM. At each stage, the student model is trying to distill 2 adjacent sampling steps. Okay, so originally the teacher sampled 2 times, okay, 2 steps. The student trying to use 1 step to learn the teacher that needs 2 steps. And the next stage, the student from the previous stage, they begins to serve as the new teacher. Okay, so in the next stage, the previous student require 2 steps, 1, 2, now becomes a teacher. So the teacher's student, the new student begins to learn in 1 step that used to require 2 steps from the teacher. So in that way, we can gradually distill the student and student to use fewer steps to predict which used to require a lot more steps. As we can see here, we can use fewer sampling steps by using the distilled version to match the teacher's model, which used to require a lot of steps. And finally, guided distillation. Remember, we had the classifier free guidance. Okay, the CFG. This was the equation. Remember this omega plus 1 and omega, right? So one is with condition, one is without condition. We have to forward the network twice. Same input, xt, with condition, without condition, with 2 constants, omega 1 plus 1 omega, we forward it twice. Can we only forward it once? So we can distill a student model, okay, that predict the subtraction from this conditioned versus unconditioned. We use just one model, okay, the student model, to learn the subtracted result, rather than forwarding it twice, once, second times. Now we just forward it once, which only need to forward once. Okay, and then step 2 is to combine that with the progressive distillation. So we can combine the best of both worlds. Combine the guided diffusion distillation with the progressive distillation, which helps with the classifier-free guidance sampling. So here are some steps. So this is using only 2 denoising steps. Pretty impressive. This is 4 denoising steps, and this is 8 denoising steps. Okay, so finally, let's talk about some acceleration techniques using sparsity and also quantization. When we are editing an image, we may not edit everything, right? So here we only add a sun on the top or a moon on the top. Okay, so it's only 1% or 2% of the pixels that's edited. So stable diffusion, when we are trying to generate a new style, we need to work on the entire image. But after we make some edit, rather than running on the entire pixels again, we only run sparsely where it gets edited, okay, to generate the sun or the moon, so that we can save the computation. Okay, originally, since only 1.7 region is edited, but a vanilla model need to resynthesis the entire image. So here we require only 1/8 of the compute. Okay, same number of steps, by only predicting the pixels that has been edited, and reuse the feature maps that stays unchanged. So originally require 1,800 gigaflops. Now it's only 225 gigaflops. Key idea: reduce the cache activation and selectively only update where it gets edited. So this is how it was done. Like the original image, this is where it gets edited. We added the to cloud here. We do a subtraction, get a difference mask. Difference mask is sparse. This is only places that gets edited. And this is the original feature map. This is the edited feature map. We gather the changes here. Okay, we pass it through the convolution, gather the changes here. And then we pass it through the convolution, only the difference, okay? Only the difference, only the diff. Rather than originally we have to run the full image with this convolution, but now only the diff went through the convolution. And then we scatter it back to the feature map and use the original plus the scattered, we get the next stage. Okay? Exploiting the feature where convolution is linear. So this is some cool result on image inpainting. Inpainting is saying we can paint something inside the image, like a photograph of a horse on a grassland. We want to paint a horse in the image. So it's only a portion of the pixels. So, but original stable diffusion require changing everything. But now we only change where it gets edited, saving about almost 4 times the latency. Another example, this is the original image. This is the edited version, and we say it's a fantasy beach landscape trending on ArtStation. Rather than compute on everything, we only compute on where it gets edited. Actually, I feel this is even better because here you get 2 coconut trees, but now it's correct. It's saving about 4 to 5x the latency running on the 3090. And actually, there is a demo here. We are drawing a piece of cloud on the top right corner. And then we can see the and that's running locally on a MacBook Pro. So acceleration techniques by using quantization. What is different here? So originally when we are doing quantization, there's no concept about time step. You have only one time step, like you are doing classification, you are doing segmentation, detection, etc. But now, across different time steps, when we are plotting the range of the activation, actually they differ a lot. So the activation distributions varies across different time steps. So the input at nearby consecutive time steps, they have relatively similar distributions. But input at distance, very like step 1, step 100, at distant time steps are distributed more diversely. So the idea is here from this paper called Q diffusion is that you have to use this time step aware quantization approach. So at different time steps, you have a different calibration set. You have different scaling factors to model the different distribution. So the algorithm has 3 parts. So from 1 to t, every certain amount of interval, you want to sample the intermediate inputs so that you can have a calibration set at different time steps rather than like detection segmentation. We just have a single calibration set. Now across different time steps, every c time step, we collect another discrete new calibration set. And this is quantization the weight. This is quantizing the activations. So the key difference is when we are quantizing the activation, it also depends on the time step. With even the same activation at different time step, we should use different scaling factor. And there's another insight. Okay, so shortcut splitting quantization. Since during the denoising phase, we're using a UNet. Okay, UNet first have this downsampling phase and then this upsampling phase, and there's this kind of bypass connections from the downsampling and upsampling phase when the feature map is of the same resolution. And when here people are observing that the distribution across different channels is varying drastically. Okay, since one of them is from the upsample layer itself, the other is actually from the downsample layer. So this bypass layer is creating a quite different distribution for this activation. Okay, so rather than using the same scaling factor and bias to characterize both the x1, x2, one from the downsample layer, one from the upsample layer, we should use separate scaling factors and biases for them. So split the activations and the weights. So one is from here, one is from here. So rather than doing quantization and using the same manner, we want to separate these two tensors to quantize the weight and activation for them separately. So they call it tensor-wise quantization. And here the weight, they are using channel-wise quantization. And the key reason is from this bypass branch, concatenating the downsample versus together with the upsample layers. This Q diffusion is actually quite effective. This is the full precision model running the prompt, a photograph of an astronaut riding a horse. Okay, so this is the full precision model. This is using Q diffusion, W4, 4-bit weight, 32-bit activation, weight only quantization basically. And this is Q diffusion with both weight quantization and activation quantization, W4A8. Quality is still pretty impressive compared with the original naive vanilla linear quantization, W4A32, even not quantizing the activation at all, the quality becomes quite poor. Okay, so we learned a lot in today's lecture, starting from the basics of diffusion models. We are having a lot of equations, but I want to remember is we are trying to predict the noise. Why do we need to predict the noise? Is that we can denoise and get a clean image. We talk about how to add conditions, 3 types of conditions, okay, class condition, and then the pixelwise condition, and also text condition. Okay, we can use the cross attention to add those text condition. And then since the resolution is too large, how do we handle that? We can use the latent diffusion. Okay, so first pass it through an encoder from BAE and work only on the latent dimension. Talk about image editing, how to change the text, and how to use the stroke to edit the image, and also model personalization. We also talk about fast sampling techniques to accelerate the sampling process by using DDIM, and also progressive distillation, where the student is trying to learn multiple steps from the teacher, and also guided distillation for guidance-free scenario where we no longer have to forward twice, but use a student to forward only once. And then using sparsity to only forward where it gets edited, and use quantization carefully to cater for to take into account for the different distribution across different time steps. All right, that concludes not only this lecture, but also the second part of this whole semester, where we are talking about the application-specific optimizations from large language model to vision transformers to GANs to point cloud, and today to diffusion models. From next week, we are going to switch gear to a new chapter, which is about training. Okay, so how do we train this model across a big cluster? Okay, and how do we perform on-device training to be able to fine-tune your model locally on your edge device? It'll be very exciting, and we'll have a lab tour to the server room to show you those beefy GPU servers. Hope you're enjoying Lab 5. Feel free to ping us if we can help you with the Lab 5. We have an office hour after today's lecture. All right, thank you, and see you next week.